Alright, so most part we use this book which is written by me. So you don't have to buy it. I will put the appropriate chapters on the class page. But I will stop you from buying if you want. But you won't, it's not necessary to buy. Oh, so now let's just start. Just taking it to me. Okay, so think about the usual two-dimensional integer lattice. And so all these are my nodes. Every person. Let's so x comma y value to z2. That's my notation for the square root vector. If they are neighbors, so if x and y are neighbors. Hopefully that is clear. This diagram of this. And edge exists between them. With probability P independent of everything else. So pictures, you could think of this as, so everything I make a red is possibly and so let's say so we keep using the word an edge is open to mean essentially that an edge exists. See, there are two ways to think about it. The edge always is present. Is it open or closed? Or you can say an edge exists or it doesn't exist. These are the same things. So whatever I'm making red are the ones which exist or they are open. And so on. This defines my random graph. On this random graph, what I want to understand is how large is the connected component. So for each vertex, there is a connected component. So for
there is no diagonal edge here.
there is no.
So every point has 4 diagonals.
Yes. So for B belongs to the C of B is all given like that. There is a path such that there is a path from B to using only the particular. That's your connected component. All the vertices I can reach. So supposing this is my origin. So in this example, what is my connected component? Let's call this 0. For my origin, how large is the connected component? Six. Okay, there can be only one answer. Why does it look like 4? Why does it look like 6? It says all possible vertices which I can reach using open edges. So I can definitely reach this guy, can definitely reach this guy, definitely reach this guy. That definitely counts 3. I can also reach this guy, I can also reach this guy. So where is this? Itself you're including. If you're not including itself, it will be 5. Otherwise, it's 6. All right. So that's your connecting. Now, still question as we've been asking. What is the largest connected component of such a graph? For each vertex, it could be small or large, but what we are interested in is, does this have a large enough connected component? So essentially, the point is, does there exist a V for which CV is large? This is very important. But this CV in distribution depends on V. Everything is symmetric. There's nothing to suggest that if I look at this node rather than this node. See, once you make a realization of these open edges, then it's a different story. So first you would first go and see which edges are red, and then look at point by point which point has the largest connected component. That might be different. But if you choose a vertex first and then make the realizations independent of that, you will not be able to distinguish. So I can essentially look at any one particular vertex and look at its connected components. So we'll define in particular, we just look at the origin and say percolation happens if the probability that the size of the connected component of the origin is greater than 0. And doesn't happen if it is 0. That's our definition. I'll find it more formally. That's what so the definition of percolation is that the probability that there exists probability that the connected component of the origin is non-zero. That's my definition. That's a Chinese definition. All right. So what can we say? Any initial comments before we begin?
Infinitely many vertices, right?
Moving on to say for any p greater than 0, the probability of percolation is 0. Right? Is always 1. Even more stronger. I was going to stop at the positive. That for any p greater than 0, the probability of percolation is greater than 0. This in fact is not correct. What you're asking for is 0.
Looking for any P for any component size, there will exist some component of that size somewhere in the graph.
That's not really true. You show it today. So what is in fact known is that P has to be exactly half. That's where the transition happens. What we will show that is too difficult and complicated. What we will show is that below 1/3, it can't happen, and above 2/3 definitely. So the right answer lies between 1/3 and 2/3. And it has been shown that the right answer, even like sharp, it's exactly not. That if you're really interested in look at detailed percolation books, there are nice books by Grimmett, and there's and we have that in the library also. Forget that. You might have seen it.
Stopper
No, I had something else in mind. Okay. All right, so let's now try to define these events. So theta p is the probability, and denote this little p to be the probability with which an edge is open. Everything depends on it. That's my percolation event. That's my probability of percolation. I'm just denoting it as theta. Please. PC or the critical probability is P of what? Okay. That's what my quantity of interest is. The smallest probability with which there are two probabilities, keep in mind. One is the probability of making the edges open, other is the probability of percolation. It clearly depends on little p, because if little p is one, the whole thing is open. So this is the quantity we are interested in. And that is not to be half. But that's too much to ask for this class. We won't go that far. Okay, so before we begin, for all of this to mean much, first we should show monotonicity of the graph, just like we did for the branching processes. That if P increases, things are not going to get destroyed. Whatever we expect to happen, it should happen also. So if suppose perturbation happens with a probability P1, or what I really want to show you, now theta P1 is greater than theta P2. So otherwise something is wrong. This is not true. If I'm making more edges open, I should expect the probability of percolation to increase. So can you give me one line argument? You've done this over and over. Why is this true?
If I already know that component,
No, it's that you can't. That's entering dangerous territories. Looking at things you can't do. But then conditioning starts coming in. But you don't want to argue this. And you've done this for other random numbers. Use the same arguments. Any idea coupling was one of them. But you can come up with any idea you want.
the expected value of connected component size will increase.
But that doesn't mean that probability is increased. Only get bounds which are uncomparable. Standard trick is to use coupling. So what is the right coupling? It's exactly the same coupling as we used before. To generate a random variable, we did something from it. Can you just follow that, you get it. It's a one line, there's nothing more. So what is the random variable I should take? Let's say you use for each edge, generate U, which is uniform over 0 to 1. That is fine. Then there are two graphs I have. One is P1, another is P2. Make an edge. UE less than equal to PI 1, I'll get two graphs. One where I use P1, other I use P2. Now can you tell me why is this true? Very true with that. Now you just have to the punchline. What is the punchline?
Just opening I equal to its also opening I equal to.
Yes. Every single time an edge is open in graph one, same edge is also open in graph. Whatever event is happening in graph one necessarily has to happen in graph, because it only depends on the number of open arcs. If on each open edge of graph one, the same edge is open in graph two, the connected component size cannot decrease. That's so that's why we have one velocity. Now it makes sense to think of this as a sharp threshold. We know at 1 it happens, we know at 0 it doesn't happen, so it has to happen somewhere. It can't oscillate. That's why it stops. Okay. So now that we know this, we're interested in finding this PC, which will not get to the precise answer. Can you guess? I gave you a hint, 1/3, 2/3. They're not very numbers are not very important. How does one do something like that? How does one find bounds on PC? Your goal is to actually precisely find this. That might be fun. But can you at least bound it? There has to be at least greater than so much. So anything which is strictly greater than 0. I don't care, 1 by 1 million. I don't care. Anything not trivial. Or less than 1 minus an epsilon. No problem. Either direction you can go. First think of what does manipulation mean and how can you control it. I'm going to go conversations now. Not very nice. Think of what kind of events will make it work and what kind of events not make it.
Theta V is the probability that the component of the origin is it has infinitely many over there. Probability. Is it the same that the probability that there exists an infinitely big component in the graph?
Yes. But that has to be connected to the origin. But it won't matter. Like what you are trying to do is not any different than this. Because you can just translate it wherever you want. But think about what does even this means. What does it mean? Essentially,
Look at it as a branching.
yeah, that's a hint. We are not going to go down that. It could be possible, but I didn't miss it. Because every time finding independent progeny is going to be difficult. So let's start with origin. 4. That one is clear. The first generation number of children is 4 times 3. Now from here onwards, they are badly coupled. So you keep making sure that common things are not counted. But then you can only go one direction up and one direction down. And each of them is just piece. Between them it becomes counted. But what you should really think about is, given that the connected component size is infinity, what does it mean in terms of reaching nodes? How far can you reach from zero from the origin? Right. So if you can do infinitely far, what necessarily has to happen? And if you can't reach infinitely far, what has to happen? This is precisely gives our condition. So if there is percolation, for each n, there is a connected path of length n starting from the origin. That has to be true. Because otherwise the connected component is small. Pick any integer. So if there is percolation, there must be a connected path starting from the origin of length, that number integer. But how many such paths are there?
At most 4 is to.
Can slightly undercounted. Slightly. Because starting 4 is correct, but then you have to avoid yourself, because otherwise you're going backwards. So only 3.
4 into 3 is to.
Right, so that way, can you use this and get an answer? So you have two things to work with. One, if there is percolation, it must be that for every n, there is a path starting from the origin, which of length n of open edges. And we also know that the total number of, or the expected number of open paths of length n is something like 4 times k to the power n. 4, because at the origin there are 4 possible directions you can go, and then from every node 3, because we don't want to come back to the same trees. So if you put these two things together, you should be actually able to get some non-trivial answer. No other computation needed. Sorry? No other computation needed. You just put these two facts together. You can get a non-trivial answer. Okay, so I will fill up the statement of the theorem after I close. Or let's say, is less than. Oh. Is everybody agree with this? That if there is percolation for each end, I should have a local path of length. So that's why I can draft probabilities around it. So theta p is less than equal to this probability. Right. Now, how can I bound this probability? Simplest one. We didn't know. Might be weak or may not be useful. Now think about the expected number. So when I'm harping on the expected number, what is the expected number of self avoiding open paths of themselves? This is a something. So 4 times 3 to the power n minus 2. Can you not put these two things together? All I want is a number one. So I have this quantity I want to control. I have this. I also have this. So if I really want to connect the two, I should think of connecting this and this. So what is the relationship between these two? The most trivial. As trivial as it can be.
That probability is equals to 1 minus probability of
This and this. This is not even a probability.
probability that this is not negative. It's positive.
It's an expectation. That's probability. Probability of having a path of length n from. This is an expected number of this. So this better be smaller than this. You just open the expectation, what will you get? If you don't see this, don't you figure it out. It's trivial amount. There's nothing to be really said. Oh, so now we have all this. Can you finish the proof of here? So where is this quantity and then goes to infinity goes to 4. Sorry? Sorry. We're going to what's the next? So now for any p which is smaller than 1/3, where is this probability?
Smaller than 1/3.
This is a decreasing quantity in p. As it goes to 0, it's clearly going to 0. But even if it is slightly smaller than 1/3, where is it going as n goes to infinity? It's being raised to power n. This guy is only n to the minus 1. So you take anything which is smaller than 1/3. And therefore the theta p then goes to infinity or p less than So what can I conclude about PC? The PC has to be at least as much as 1/3. Because for any value which is below 1/3, the probability that there is percolation is going to be 0. And the whole definition for the probability of percolation should remain greater than 0. Is the idea clear what we are trying to do? The other direction is still like not very complicated, but more interesting. It was rather too easy. Now you can start strengthening this level if you want. Anyway, we want to bridge the gap from the sandwich of 1/3 to 2/3 all the way down to 1. We can do it. Is the idea clear what is going on? That's okay. That percolation implies something. Can you control those? That's the percolation implies that for every n, there has to be an open path of net. But the expected number of paths is only so many. So if you want percolation, it better be that this quantity cannot go to 0. Very simple. Okay, so this was the. Now let's. That was converse. This is forward direction. You see that most. This is the positive side. That after 2/3, I will definitely see theta p to be greater than. Now what can I do? Now I can't use the fact that if there is percolation, this is bad. Now I have to see if there is no percolation, what ought to happen? That's the event I'm going to control.
Component whole thing is surrounded by edges that are not open. It's finite.
Make it more formal.
A boundary of
Yeah, how do you define boundary? It's a fruitful idea. Essentially, always think of this as escaping. The way I always think about percolation is that you put a box, which we typically call as the bounding box, around the origin. Think of the box as a square box. It is percolation. You can always escape to the other side of the box using an open path. But if there is no percolation, you have to remain within. What he's saying is something similar, but now you have to define the box appropriately.
there exists.
It's not sufficient to say that there exists a bounding box where all the edges are closed. Right? Because I can always go through the. You understand what I'm saying? It's not, but the idea is not bad. You just have to tweak it a little bit. It's not sufficient to just say that this all these vertical edges and all these horizontal edges are not. Then percolation will not happen. Because on that point, there is a edge going out this way. Suppose you say this is my origin. This edge, this edge, this edge, this edge. Suppose all of them are closed. Does it mean that I cannot go to infinity? No, because I can always leave this. From this point onwards, rather than escaping this way or this way, I'll escape it this way. Just saying that a box around the origin and all edges are closed is not sufficient. You have to slightly tweak this idea, and then you can claim that if that exists, then there is no problem. For the moment, we are stuck because I can always escape it via this. This one, this one, this one. Because internally you are not seeing. If you say internally everything is closed, then it becomes problem. That is one possibility. Just along the boundary of the box, that's not.
Along the boundary and out of the boundaries.
Yeah. Think of translating the lattice itself by half comma half. Just take every point and add. So if the coordinates are x comma y, just make it x plus half and y plus half. That will give you a new lattice. Now can you think of the idea here of the new lattice and then say something?
Basically we will make a loop which will go, this will intersect the one.
Yeah. So all the vertical edges will intersect the horizontal edge.
All the one which are intersected by this loop, if they don't exist, then I have a conflict.
No, because I also have to first I've just translated it. So for the moment, the vertical edges have nothing in common with the horizontal edges. So I also have to connect them on. If I just translate, the edges intersecting each other, the horizontal and the vertical, they're independently open and closed.
I'm saying that the loop you made, we can make a loop which intersect all the vertical points on the top of it and the horizontal points.
I'm not following it. So just tell me let's start.
In the middle of the
So we-
bracket.
Yeah, okay.
On the top.
So keep telling me up, down,
Up.
right, left. Okay, I reach here.
Up.
So I got here.
Half.
What is half?
In between that and the center.
Oh, this point.
No, not here. Up, half.
Even
Yeah,
further.
and make a loop which is concentric to this one. Yes. If all the bonds which are intersected by this loop are closed, then I have around 5.
Perfect. Now how do I get that? Is the question. You'll have to not only just translate, you also have to connect. If I just translate this, what are going to intersect are not really connected to each other. So if I just translate this point here, a horizontal line is going to intersect a vertical line.
Yes.
But if you look at the original graph, an horizontal edge was open or horizontal edge, vertical edge was open, but independent of each other. So that's not going to be good enough. So if I'm translating, I also have to define something. When is my translated edge open or closed? So you're almost there. So your circuit idea is correct. That if I translate it, now it's trapped. Because earlier what was happening was that this was an escape point. But now controlling this edge as well as this edge, now it's completely trapped. But now to make use of it, you'll have to use this translation and an additional property that when is an edge actually open, it then translated lattice. You're going to get two lattices, right? One the original one, other is the translated lattice. Now you have to define each edge in the translated lattice to be open or closed. How do you define that in the question? So we use your idea, there's only one way of doing it. We want to trap it in this translated lattice. So think of a lattice and a translated lattice. Don't think of a lattice where I've already defined an open and a closed edge. Think of a lattice. Think of the translated lattice where every point is shifted by half comma. Now go back to the original lattice and make these edges open or closed. Depending on that, what should I do to the second lattice's origin? Because in the translated lattice, there are edges intersecting each other. If your bounding box idea is going to work, you need something very specific.
What are we doing? We are seeing if there is no percolation, then there exists a box.
If there exists such a box, there is no percolation. It will be direction. So we'll try to say that this doesn't happen as long as P is greater than 2/3. That's the way. So again, we're looking at controlling a bad event. So that bad event, if it doesn't happen, then it implies percolation. Because there is no such closed circuit of any length, you'll have percolation. We'll try to bound the whole problem, any possible box, not just one box.
So it is possible to have no such box and also not have.
How is it possible?
Your boxes are all
No, we'll not restrict ourselves to only square box.
rectangles.
We'll all possible circuits. That's why we use the word circuit. But the basic idea should be there. We make it more important. Because the shape in which you can come around doesn't have to be nice. But the broad idea should be clear. What are we trying to do? All we are trying to do is to make sure that the probability of finding a closed box is not too large of any size. Okay, so
For each vertex in the circuit, you also want maybe two more edges to be not good.
okay, so now let me draw this again. Fewer.
If I take a dual lattice and connect the vertices, if there is no open edge between them, then I'll get
Let me just draw this. I'm just. This idea that you working already goes, it sounds very essential. Okay, so this is your dash. It's also called a dual lattice. We call it translated lattice. So. It is. Dash. Bad notation, but let's live with it. Okay, so where is origin going? So new origin is here. It's shifted. Now, what the most rate was possible to apply to this. So let's say this edge was. So make this edge blue. That's my definition of dual lattice. If my original lattice is the black lattice, any particular edge was blue with probability P. To get to my dual lattice, I just transferred everything. Now I'm defining each of these edges to be blue or not blue. So I define it to be blue if it intersects a blue edge. Simple as that. Otherwise, it is closed. And this is required for if you want to use the idea he proposed. That if there is this closed circuit in this dual lattice. Now think of the dual lattice having a closed circuit. We'll define what circuit is, but think of a box. So if there exists, so now this is the box you will be thinking about. Let me write this first, dual lattice. Make in the dual lattice. Edge open. If it intersects. Make it depend on the.
But in this way, the graph will be changed.
Which graph am I interested in? The black one. I want percolation on black graph to be controlled. I'm defining whatever artificial for myself. The condition will be that the black graph does not percolate as long as the red graph has a circle or a box surrounding the origin of the black graph. Right? Because how that's why this connection was important. Now, whatever defined that a blue edge becomes an edge becomes blue in the red graph
If it intersects.
if it intersects with the blue edge. So now, if all of this was not blue, what does it mean? So think of this. If all of this is closed, what does it mean? There's no way out because all of them are not blue. There's only way in which you can. What color is it? Orange. Green. Yeah, it's very difficult for me to make this color sound. So if I say something random, this in between red and green is very difficult for me. So that's why I don't use it if you're not noticed. I always go for blue or red. This is green, so I'll stick with it. So this particular box, if it has not a single, like all of them are closed, there is no way percolation there. So that is why it's interesting to look at this dual lattice and the number of the probability that there exists a box of finite length where all these edges are closed. This will ensure that there is no percolation. What is this green dabba? Green box means that all these edges are in fact closed. If such a thing exists, what can you say about the connected component of the origin in the black graph? That's the most important fact. If you notice that correctly, we are essentially on our path good to go. Is that clear? That if there exists such a orange box, the orange box by definition means that all the edges, the orange box is defined with respect to the dual lattice. It means all these edges are closed. And if such a thing exists, what does it mean for the black graph? That there is no way out of this box starting from the origin. So necessarily the connected component of O is smaller than like the number of nodes contained in this box. So all I need to care about is what is the probability that exists any block, any such orange green box of any size. If I can control that probability, I should be able to say that, well, the probability with which such a a box exists for any n is smaller than 1, then I can do that. Because anyway, I'm interested in probability of percolation to be greater than 0. I'm not interested in probability of percolation to be 1. So it's the main idea clear. First idea is dual lattice. Why dual lattice? Because of the observation you guys made that if I want to stop you from escaping from origin to outer world, all I need to do is to come up with a translation to cover for this escape out. If I just looked at the original lattice itself, however you define your box is always based out from the corner points. But if you translate, we are also cutting off your escape routes. That's the main reason for defining a translation. And now it makes sense if the translation, this edge is open or closed depending on what was open or closed here. Because otherwise it will not mean anything. So that's why that is natural. The non-trivial idea is to make sure that these escape points don't exist. And the clever fix was to do half an hour. It was good that you already spotted that. Okay, so now they were given all the hard work. How do I put down the actual numbers? The final answer you want is 2/3. Why 2/3 the question? Which one to do just for box, like square boxes, let's do it for square boxes. It's not, it's easily extendable to any shape, which is starts from the same point and comes back to the same. So work with the length rather than the area, theoretical one. But the idea is the same. So even if you want to work with, so all I have to show now is what is the probability that there exists a box of size n which is closed in the dual lattice. That's all I have to worry about. How many boxes exist of length n? So only count rectangles and squares. Or if you want to first, as a first step, only count squares.
Perimeter is it?
Perimeter is n, whatever that is.
Where n by 4 whole squares. That's that origin is inside the square.
So what was the answer?
Side, so if you have a square with perimeter and side length is n by 4.
Correct.
And I'm counting how many squares there are of that size.
Of perimeter n.
Such that the origin
Is
is
correct.
contained inside the.
Yeah.
So n by 4 whole square.
What? Again.
Translate this square. N by 4 is horizontally and n by 4 vertically.
Yeah.
That's why n by 4 n square by 6.
N square by 60. Okay. Fine, go ahead. Let's see. If you can show 2/3. I'll do everything. If you don't give it, giving you enough time to think about it. So if you write it out, you know, get a feel for it. So currently, all I'm asking is to do something simpler. There are many other ways in which you can have a closed loop around the region. All I'm asking you to do currently is that let's just worry about only the squares. There are squares, there are rectangles, there are all parts of odd shapes, which I have to worry about. But if you get the squares right, order-wise, it should not be too worried. Slide those things. Okay, let's try. Yes. What if we define it? You don't need to do it separately for squares. Circuit in Z2 or D2, this line is the cell of variable. And rotate part. Connected doesn't mean open, okay? Connected just means that that's what I began with, that this edge is always present. Is it open or closed is on top of it. So connected means I can't say a path between this and this and this and this. It has to go from here to here. So that's what it means, a connected path. Is it open or closed? It's in addition to that. So connected just means that it's a feasible path. Let's call it feasible. It's possible to have such a self-avoiding connected path. Into or into the structure. Starts and ends and save vertex. Others here. So define a circuit for me. I'll just draw it so that we know what a circuit is. Right. Suppose I'm starting from here. Where should I go? This is the circuit. Started here. I'm not necessarily around zero. I just drew it so that I can use it. But definition does not require it to be around zero. It could be anywhere. It's just that it's self-avoiding. It doesn't cross each other. That's all. Okay. So now, given that this picture is available with us, how many closed circuits can exist which are around zero? That's really what we are interested in. You're thinking of boxes and rectangle. No, you're not a worry about that. All I'm going to play around with is length n. So suppose the length of this circuit is n. How many possible such circuits exist around the origin? So then I can just throw in p to the power n. So 1 minus p to the power n. So say that all of them, all the edges on that circuit are actually closed. See, what do I want? I want every single edge on this to be closed so that there is no way out from the origin. So if I can upper bound the total number of possible circuits, I know exactly what is the probability which a particular circuit is closed on. A circuit is closed if all edges on the circuit are closed. Simple as that. I can define it first. So circuit is defined to be closed. Every single edge on the circuit is closed. So it is sufficient to upper bound the number of possible circuits, and then I just multiply 1 minus p to the power n.
I have it out.
Yes, go ahead.
This connected thing and open.
Is the completely different thing. So you should think of this as feasible.
Means basically there is an edge. That
So
is
I don't want to say an edge. That's what I'm trying to say. An edge is same as having an open. So think of Z2 on its own.
okay.
Forget about open. Just Z2.
Hmm.
The way I start drawing the black line. So the existence of black line means that there is an edge. Right?
Okay.
So I can traverse it or not. That's defined by being open or not.
Okay.
But I can't have a path like this and this without having anybody in the middle. That's what it means feasible. Is it like even after making open, can I actually travel it or not? This is slightly a subtle point, and there's two things are on top of each other. So this has nothing to do with an edge being open or not. Now I'm defining in addition that the circuit is closed if every single edge on the circuit is closed. So all I want to find out how many possible circuits there are of length in surrounding the origin. Give me an upper bound. It doesn't have to
Don't
be.
look at self-providing.
Yeah,
So
okay.
if you don't look at beginning and ending at the same vertex,
Okay.
this is what we had 4 times 3 to the image.
But why is it not otherwise also the same?
No, the 4 times 3 raised to the minus 1 was how many paths you have length.
Correct. So you just have to augment that a little bit. So that's why I extended the x-axis for a reason. So consider how many different possible locations a circuit can cross the x-axis and the circuit's length is n. Locations.
Right. To the right and right.
Can it be anything more than that? That is, we multiply into whatever number you get. It's very simple. So any circuit of length n around the origin can cut x-axis at most n different places. And you already had that how many possible paths of length n, self-avoiding paths of length n can exist. So if you put them together, you get that the possible largest number of, because from where you start your circuit, you can define anywhere you can start. There are possible 4 options of going anywhere. But thereafter there are exactly 3 of them. And the length is n. Now you essentially you're just looking at how many different ways I can translate this. And there are at most n such ways. So for each path, which is of length n essentially, you had 4 times 3 to the power n minus 1 possibilities. And in addition, you have allowed this translation phase. So the maximum number of circuits surrounding the origin of length n is at most n times 4 times 3 to the power n minus 1. Not convincing.
So,
No, think about it. Why do you want to think about it?
horizontal vertical is symmetric, right?
Yeah, but why counting one is not sufficient? What do you want to count the y-axis?
So what you're doing, once you fix the shape, then you are translating it.
Yeah, but that's not how we think about it. See, the length of the path is that much. How many possible ways in which it can go anywhere in the world? But the ones I'm interested in surrounds the origin. Right? So it has to cross the x-axis somewhere. That's all I need to know. But if it doesn't cross x-axis, there is no way it can surround the origin. That's all. There are many other paths. Circuits of length n exist, a lot of them. The ones surrounding the origin is what I'm interested in. So what you're
It
saying is
also needs to cross the y-axis.
it will, but I don't have to count both simultaneously. Because one is unnecessarily counted. Because any circuit which crosses an x-axis is sufficient to count.
So if just take this simple example, take a square.
Yeah.
There are n square different translations you can do.
Okay, but all of them cross the origin.
Yeah.
But then you're already overcounting it in 3 times 3 to the power n minus 2. Somewhere you overcount. We've already given you a lot of room when you started looking at the paths of length n itself. You can convince yourself that this is not more than all you need to worry about is where it crosses the x-axis. So what you're saying is you're just counting the number of boxes. But if you don't allow for what you already counted for, that will be seriously overcount. But slightly weaker. All we are saying right now is that a closed circuit around the origin must cross the x-axis. That much is clear. By the same logic, it should cross y-axis. How many possible places it will cross the x-axis? First fact, closed circuit has to cross x-axis. Is that clear? How many different places can it cross? Can it cross arbitrarily far away?
For length and you cannot.
So how far, if the length is n, how far can
Right.
you can go this way and might do this? How many total possibilities there? And each possible at each point of time, how many different directions you can take? Essentially three, other than the starting. If you put these three things together, that's sufficient to count the total number of circuits. Closed circuits, circuits around the origin. And a circuit to be closed, you need that probability to be 1 minus p to the power n. So what we end up getting is expected number of closed circuit. N. Or and okay. Now what should I do? This case requires a little more care than the previous. We are actually not done yet. All we are trying to say is that the expected number of closed circuits of length n around the origin is as we will go because now I need to show percolation. I need to do some more work. But like this relation, what is the appropriate relation? So what I have essentially done is bounded this quantity. I want the in between quantity which connects the percolation itself. What is the in between quantity? Think of the following quantity. Probability of having closed it. When you think of a relationship between these two quantities, essentially the same. Larger. Okay. Now, thinking what I've got is I've computed the probability of this. But now I have to run over all possible else. Basically, what is going on? I don't want this to be true for any n. For percolation to happen, I want to control this probability for all possible ends. We want to sum it over. So let's call this P closed and for relationship. P and for all possible n. I want this to be, at least for the moment, finite. Then we'll worry about something smaller than 1. That's the bound I have. When is the bound even finite? That's the first thing to check. So summation for lines in speed of this need not be less than 1 always. But we'll take care of that. As long as it is at least converges. So for what value of P this converges? Give me the most trivial value you can find. That's not too hard. This is increasing as 3 to the power n minus 2. You can possibly say 3 to the power n in the worst case. And then this is 1 minus p to the power n. So what's your expectation? Not in terms of that what should do? 2/3 So for P greater than two-thirds, this should actually converge. What should I do? I really want probabilities to be less than some quantities. See, I want this probability to be smaller than a number which is smaller than 1. That I won't get from here. But what will I get from here? What does this mean? That if some of this is greater than some quantity, can I say if I start from somewhere else, I will get this sum to be smaller than, let's say, 1/2. So if this is true, can I claim that for n equal to some n critical, it's going to claim is less than 1/2? I can. Now, can you use this NC to build an argument saying the probability of percolation as long as P is greater than two-thirds. See, when P is greater than two-thirds, this probability is finite. So exists an NC. Now use this NC to claim that the probability of percolation is greater than zero. And don't lose the meaning what our N was. NC was length of a closed circuit. So what it also means is the probability of having a closed circuit of length NC around the origin is less than half. That's precisely what this means. This is okay? Not okay.
No.
If this is finite,
Yes.
what does this mean? Can I find an NC
Yes.
such that this is true? That's all. Why am I doing this? That's a separate story. Because if this itself was less than 1,
So if this converges, then
but convergence need not be less than 1. That's all.
if this total probability converges, then there is no convergence, right?
See, here, if this summation was less than 1, I could have said something. It's only converging. I don't know where it is converging. It could be larger than 1, in which case I will not be able to say it. So all the now remaining things have to take care of that. That's why we are expanding from. So we're going to throw away the fact that we're going to count small number of circuits around. I will take care of them separately. I'm saying the probability of having a closed circuit of length large enough around the origin is small enough. And for the length small enoughs, which are not being counted here, I will worry about separately. So this is again a standard. This was not clear like it took people some time to figure this trick out. That this can be done. So what you should really treat this sum is the probability of having a closed circuit of length, any length greater than NC around the origin is less than half. That much is known. Now you have to worry about of lengths NC and less. What can you say? And always remember P is greater than two-thirds. Because otherwise this itself doesn't make any sense. So this clearer in head. What all I'm saying is that when P is greater than two-thirds, the probability of having a closed circuit of length more than NC is smaller than. If it was true for length 1 and beyond, I was done. But I would not be very lucky. But I'm almost there. Because my end goal was very modest. My end goal was to show that probability of percolation is greater than 0. If I had set a constant as a goal for myself, that would have been very hard. The goal itself is modest. So what is the probability of smaller things? That's all you have to worry about.
This sound right out to NC.
But then we know is more than like you add everything together, then we know it's not going to work. And that is coming from because of our very loose bounds. The probabilities have been upper bounded by expectations. So that is where there is slack, which you need to tighten. If everything was equality, there's nothing to tighten. We have essentially upper bounded probabilities by the expectation which is much larger. So now you have to recover the lost ground. For beyond NC, it's okay, but below NC, it's not okay. So below NC, you have to go back and see what we are missing. That's all. So think of a square box of size NC itself, surrounding the origin. One single box. Can you say something interesting and finish that? So it's just side is NC. Perimeter four times.
What is special about NC?
NC is the ones we are interested in. That's why it's beyond NC already.
So this, if P is greater than 2/3, then the probability of having a circuit of length N is non-zero, right?
No, no. What we have said so far is that P is greater than 2/3. Then probability of finding closed circuit of length greater than equal to NC is less than 1. That's all we have shown so far. So we have taken care of larger numbers. We also need to take care of smaller numbers. We're saying the closed loop can't be too big. The closed loop will be small. Who will take care of that? That's what we're doing. Now the point is that once you have a constant NC is bounded, aren't we done? You should just think about that. What was my trouble, right? Really, my trouble really was that NC could be really large.
Yes.
But now once you have bounded NC by a finite quantity, then there's not obvious what to do now. So in particular, look at the box, which side box rather square box, which side NC side. What magic can you do and say? So suppose every single edge of that box is open. The square box with side NC. What is the probability of that happening? That is P times P to the power and NC squared. But that's finite again, but NC is finite. What can you say about the population probability? You all we're trying to bound is the probability that it exists a closed circuit of any length. This so far is clear. Now what is happening for lens below NC is a question. So if I define a square box centered at a region with side NC, what is the probability that every single edge is open? P to the power NC square, which is finite. I don't care how much it is. It's not going to zero because NC is a constant. Now, can you stitch these two things together? This fact, which is the last one here, and the probability that a full box of size NC is open, is also a constant. This is a constant, that is a constant. Can you put these two things together to show that percolation probability is one? So if the full box NC by NC block is open, all of these are open. What does it mean? Every single edge is open here. There can't be closed circuit. Any closed circuit has to be from the outside. So, what is the probability that there exists a closed circuit of any size now?
Would be more than.
More than one. I don't care more or less. What do I want? I want this probability to be less than one. That's all. That there exists a closed circuit of any length to be less than one. And I have these two facts now. And the probability that this box, every single edge is open is p to the power, whatever that number is, NC square. And for any NC large, any number larger than NC, it is less than or equal to half. So what is the probability that there exists a closed circuit of any size, of any length?
After solving experience.
That's all. It's not any important number, as long as it is less than one angle. See, again, follow what is going on, not the numbers. What we've been able to achieve here is that for large enough circuits, any number beyond them, probability of existence of them being closed is less than half. And why there was a slack? Because the way we upper bounded it. We upper bounded the probability with the expectation. If it was all equality, then there is no room. Wait. To improve. Why am I improving? Because for numbers smaller than NC, I'm going to look at the actual graphs. So here, if this was greater than 1, and I could not do anything, then I was stuck. But the fact is that there's so much lag going on. So there exists some constant NC, which is finite, beyond which you will not find a closed circuit of that much length with more than half the probability. Now, for anything before that, I can always say, what is the probability that every single edge inside that box is open? That probability is p to the power NC square, because that's how it is. Now, all you have to notice is what is the probability? You put them together. Greater than NC is less than half. Smaller than NC it is. Right. So what is the overall probability of finding a circuit of any length? As long as you can convince yourself it is less than 1, we're done. So I'll write the final statement. Let you convince yourself. Any closed circuit into the link. Is it okay? That's okay. That's this probability is finite, this probability is half. Both are probabilities in when you get some turn it around. So essentially everything is flipped around. If this doesn't happen, then formula. And this is not happening. If this doesn't happen with non-zero probability, that happens with. Okay. So that's what it is. So the takeaway is really that you look at circuits of large length first, make sure that you can come up with some finite number, and below that things are easy. All we really have to do is to establish that NC is finite. That's really trick to do this. Because if NC is not finite, this probability will possibly go to zero otherwise. Because if this is too large, the box I'm looking at, then that probability goes to zero at a very fast rate, p to the power n square. So that's why NC has to be a finite. All right, let's stop here.